In this video, we're going to take a look at Hess's law in regards to thermodynamics. So quickly, we want to do a little review about the enthalpy of a reaction because this is going to be important for us solving for Hess's law. Recall that enthalpy is proportional to the amount of reactant that is involved in a chemical equation. So for this balanced chemical equation of the combustion of methane, 890 kilojoules of energy are released. We know that they're released because it's a negative value. So that means for every 1 mole of methane, this much energy is released. For every 2 moles of oxygen, this much energy is released, and so on and so forth. So if we are to change any of these coefficients, we have to change the amount of energy that's given off as well. So the example here is we see from the balanced equation, we have 1 mole of methane. So we're giving off negative 890 kilojoules of heat. If we changed that to 2 moles of methane, we would now be releasing twice as much heat. So we're just taking negative 890 and multiplying by 2. The second aspect here is that if we reverse the reaction, which just means that we take the products and turn them into the reactants, and the reactants become the products, which you can see here again for the combustion of methane, but now it's the products, carbon dioxide and water, coming together to make methane and oxygen. That means that our sign is going to change. It's still the same amount of energy, but since we're reversing the reaction, we're reversing which way the energy is moving. So now it is an endothermic process. And lastly, we have to pay attention to the states of matter. So we see here that if we compare this reaction on the bottom to the first reaction on the top, everything looks the same except for the water. Up top, we have liquid water. Down here at the bottom, we have gaseous water. And so we can see that our enthalpies of the reactions are different depending on the states of matter. So all of these pieces are important for us to carry out Hess's law. So now let's take a look at what Hess's law actually is. Hess's law states that if we see one chemical reaction occurring in several steps, then we can find the enthalpy of the overall reaction by adding up the enthalpies of the individual steps. So we can see in this example here, we have our equation of the methane being combusted, and we're forming that gaseous water, which was the very last equation that we saw on the previous slide. But let's say that this doesn't naturally happen. Instead, it's made up of these two smaller steps. Step 1 is the combustion of methane into making liquid water. And then step 2 is converting that liquid water into gaseous water. So if we know the enthalpies of both of the smaller reactions, we can find the enthalpy of the overall reaction. So here is our overall reaction. How do we find this enthalpy? We add the two together. So it's going to be negative 890 plus 88, and that gives us our negative 802 kilojoules, which is what we saw on the previous slide. But it's not always that easy. Sometimes we have to rearrange our smaller equations or the individual steps in order to create our overall equation. So let's take a look at some of the rules or some of the steps that we can take in a Hess's law problem to try and figure out the enthalpy of an overall reaction based on smaller individual steps. So these are the steps that I personally like to take when I'm dealing with a Hess's law problem. There are multiple ways to deal with a Hess's law problem, so this is not the end-all be-all, but this is a way that I have found is often helpful and able to make sure that you're covering all of your steps. So step number 1 is going to be to make sure that the reactants in the overall equation are also reactants in at least one of the individual steps. Now, these steps that I'm talking about right now aren't going to make a whole lot of sense until we do an actual example. So for right now, just write down the steps and we'll take a look at how these steps can be followed. But first of all, we need to make sure that the reactants in the overall equation are also reactants in at least one of the individual steps. The second part is to do the same thing, but for the products. So once we know that we have all of our reactants in the proper spot, we have all of our products in the proper spot, now we need to pay attention to coefficients. So the next two steps really can be done in any particular order. So I'm actually just going to write it as one step, even though there's two parts to it. The first part, which again doesn't necessarily have to be done first, but it's just the first thing that I'm going to talk about, is we need to make sure that the coefficients in the overall equation are the coefficients in the individual steps. But along with that process, we have to pay attention to and cancel out intermediates. What is an intermediate? Well, an intermediate is any substance that appears as a product in one reaction and a reactant in another. In other words, you know that something is an intermediate if it shows up on both sides of the arrow in different reactions. So what do we do when we see something that is on the same side of the arrow or on different sides of the arrow? So if we have the same substance on the same side of the reaction arrow, that means we add the coefficients together. If we have the same substance on different sides of the reaction arrow, we subtract the coefficients. Your last step here is to make sure that all you have left are the substances in the overall equation. Make sure that everything else gets canceled out. Once you've done all of these steps, your last piece of information is to sum the enthalpies of the individual reactions. I know this looks scary. It looks like a lot of steps. It's going to make more sense once we actually do some practice problems. So I'm going to switch back over to the slides. Feel free to pause the video if you need to keep this slide up. So let's take a look. We have here two different examples. So we're going to start with the first example here, which is just these three equations. So I separated with a line so that we know which are the individual reactions and which is the overall. So the overall reaction is the bottom one underneath the line. Just like in a math problem, you would put your two pieces together and then equals line. So here are our two individual equations. So I'm going to mark them just so that you remember this is our first individual step, our second individual step, and then our overall reaction is this. That's our goal. We're trying to find the enthalpy of that reaction. So let's take a look. From our steps, the first piece of information we needed to do was make sure that the reactants in the overall equation are reactants at least in one of the individual reactions. So let's start with carbon. We need solid carbon to be a reactant somewhere in these two reactions. We can see solid carbon is a reactant, so we can check that off our list. Moving on to oxygen, we know that we need O2 gas to be a reactant somewhere in these two reactions. We can see that there's O2 gas in both. Right now, we are ignoring coefficients. We're just paying attention to the substances. Coefficients come in a later step. And then that finishes step number one. So we have carbon as a reactant, we have oxygen as reactant, so we're good to go there. Now we move on to step two, which is to look at our product. Our product here is carbon monoxide gas. Do we see carbon monoxide as a product in one of our smaller reactions? And in this case, we would say no. Carbon monoxide is actually a reactant, but we need it to be a product. So in order for us to convert this from being a reactant to a product, what we're going to do is reverse the reaction. So I'm just going to show little reversing arrows. So that's going to change this reaction. And so because I don't have a whole lot of room, I'm going to rewrite it up here. So it will become CO2 gas makes carbon monoxide gas plus half an oxygen. That way we get rid of this. It's no longer important because we've rearranged it. And then what happens to the enthalpy of a reaction when we reverse a reaction? Well, we saw in an earlier slide that when we reverse a chemical reaction, the enthalpy changes sign. So the enthalpy is now going to be positive 283.0 kilojoules. So we can forget about that. So now all of our reactants are in the proper spaces, all of our products are in the proper spaces. Now you might be thinking, well, wait, we just changed it so that now oxygen is a product. Doesn't it need to be a reactant? Yes, but don't forget we also have it as a reactant here, so we're still good. We're still okay. So we have all of our substances on the proper sides of the arrow. Now what we're going to do is take a look at getting the correct coefficients and canceling out or adding together any substances depending on which side of the arrow they fall on. So we need, looking at carbon first, we need one carbon. We look at where carbon is in our individual steps, and we have one carbon, so we can move on. For oxygen, we have half an oxygen. That's what we need. Well, we see that we have one oxygen here and half an oxygen here. but they're on different sides of the arrow. Oxygen here is a reactant. Oxygen here is a product. Based on the rules that we just discussed, if we have the same substance on opposite sides of the arrow, which we do here, right? Oxygen's on the left side of the arrow here. Oxygen's on the right side of the arrow here. If we have the same substance on different sides of the arrow, we subtract their coefficients. So we have a coefficient of 1 for this oxygen and a coefficient of 1/2 for this oxygen. So 1 minus 1/2 gives us 1/2. So that's going to completely get rid of this oxygen, and we're going to be left with half an oxygen here. Because 1 minus 1/2 gives us 1/2. So our oxygen is good. Then we look at carbon monoxide. We need 1 carbon monoxide, and we find carbon monoxide here. It's already 1 carbon monoxide. So that's good to go. Nothing extra that we need to do there. Now we need to get rid of any other intermediates. And you can determine if something is an intermediate based on if it shows up in the overall equation. So is there anything that shows up in the individual reactions but does not show up in the overall reaction? Your answer should be carbon dioxide. Carbon dioxide shows up in both of the individual reactions, but not anywhere in the overall reaction. We see that carbon dioxide is on either side of the arrow. For the first reaction that we have written here, it's on the left side. For this reaction, it's on the right side. So again, we subtract coefficients. 1 minus 1 equals 0. So both of these carbon dioxides cancel out, which is why they do not appear in the overall reaction. So all that we should have left is carbon, half an oxygen, and carbon monoxide. And that is all that we have left. So to find delta H, we add up the enthalpies. So it's positive 283.0 minus 393.5. We put those two together, and let's see what we get. I have negative 110.5 kilojoules, and that would be your answer. So when you're solving for a Hess's law problem, your purpose is to find the enthalpy of the overall reaction. A lot of steps that we need to take in order to get there, but that's the goal of Hess's law, is to find the enthalpy of an overall reaction based on the individual steps. So we have another example here. Let's check it out. We're going to start with our original steps. Again, let me just identify these are the small steps or the individual steps, and then we have our overall reaction at the bottom. So let's start by looking at our reactants. So we have carbon as a solid as one of our reactants. We look in our 3 reactions. Do we have carbon as a solid? The answer is yes. It is carbon solid as a reactant, so we can move on. Again, we're ignoring the coefficients for right now. Then we look and we need hydrogen gas as a reactant. Do we have hydrogen gas as a reactant in at least one of the other reactions? Yes, we do. We have it right here. Then we have this compound, C2H2, which you have not learned the name for, but this is called acetylene. And for this particular gas, we need it to be on the product side. So we ask, is it a product in one of our smaller reactions, or one of our individual reactions? And we see no. it is a reactant. So that means we need to change it. We need to make it into a product. So just like we did for our first example, we're going to reverse this reaction. So I'm going to rewrite it as 2 carbon dioxide plus H2O makes C2H2 plus 5 halves oxygen. So what happens to our delta H? It now becomes positive 1299.6. And we can ignore this entire equation now. It no longer matters for this problem. So now we have our reactants in the correct space. We have our products in the correct space. Now we can look at coefficients. So for carbon, we need to have a coefficient of 2. We look for carbon, and the only place where we see carbon is right here. And it currently has a coefficient of 1. So we need to multiply this entire equation by 2 in order to give this a coefficient of 2. So anything that we do to one element or one substance in a reaction, we have to do to everything in that reaction. So this is going to become 2 carbons, 2 oxygens, and 2 carbon dioxides. What happens when we change the amount of moles in a reaction? We have to do the same thing to the delta H. So this delta H is going to be multiplied by 2 as well. So we take negative 393.5 multiplied by 2. Our new delta H is negative 787, and this number goes away. So now we have our 2 carbons. Our next one is hydrogen. We need 1 hydrogen. So we look for hydrogen in all of our reactions. We only have 1 hydrogen. That one's good to go. We look at our acetylene. We need 1. We look for acetylene in all of our reactions, and we can see we have 1 acetylene. So everything so far looks good to go. Now we need to get rid of anything that does not appear in the overall reaction. So what substances do not appear in the overall reaction? You should see, for instance, carbon dioxide does not appear in the overall reaction. But we have carbon dioxide here, and we have carbon dioxide here. We have 2 carbon dioxides on the left side of the arrow, and 2 carbon dioxides on the right side of the arrow. So since they're on opposite sides of the arrow, we subtract. 2 minus 2 gives us 0. So both of those carbon dioxides cancel out, which is why they do not appear in the overall reaction. Another substance is water. We have liquid water on the left side of the arrow here, and liquid water on the right side of the arrow here. Again, opposite sides of the arrow, so we're going to subtract. 1 minus 1 gives us 0. That's why water does not appear in our overall reaction. The last thing you should notice is oxygen. And for oxygen, we have a lot going on here because we have oxygen in every single reaction. So if we look at our first reaction that we have written here in the blue, we have 5 halves, and that's on the right side of our equation. In our second equation, we have 2 oxygens, which is on the left side. And in our third equation, we have half an oxygen, which is also on the left side. So here we have 2 oxygens that are appearing on the same side of the arrow. They're both on the left side of the arrow. Substances that appear on the same side get added together. So these two oxygens together give us 2.5. Well, 2.5 can be written as an improper fraction of 5 halves. Well, guess what we have on the opposite side of the arrow? 5 halves. If you don't want to think about it in terms of improper fractions, we could start by just canceling out one of the oxygens. So for instance, we could take a look at this first oxygen, say it's 5 halves. This one down here is 1/2. So if we get rid of this 1/2, that will leave us with 4 halves, which we know equals 2. So now what's left, these two oxygens can cancel out with these two oxygens. So everything has been canceled out except for our 2 carbons, our 1 hydrogen, and our 1 acetylene. So now we add together. So it'll be 1299.6 minus 787 minus 285.8. Let's put that together. And so that gives us an answer of 226.8 kilojoules. And that's our enthalpy for the overall reaction. Now, a question could sometimes come up, all right, that's all good and dandy, but where are these numbers coming from? These numbers are coming from the enthalpy of formation, or the heat of formation. So let's take a look at heat of formation, which can sometimes be thought of as a more simplistic form of Hess's law. Now, for the delta HF, which stands for the heat of formation, by definition, this means the enthalpy when 1 mole of a substance, particularly of a compound, is made from its elements in their standard states. We know that it's asking about standard states because it has this little circle here. This little circle is known as naught. And you can see that up here as well. So anytime you see something delta H naught, in this case it's delta HF, but anytime you see delta H naught in general, that's going to mean the enthalpy when all reactants are in their standard states. And you can see here that standard state means in its pure form at 1 atmosphere of pressure and 298 Kelvin. This is important because 298 Kelvin is 25 degrees Celsius, which is known as room temperature, and 1 atmosphere of pressure is known as a normal atmospheric pressure. So essentially what we're saying here is how would you find given elements in nature naturally found? Now it says here Appendix C. That's actually not the case. Appendix C is from an old textbook, but you have the enthalpies of formation in your textbook if you go online and check out the resources there. But notice that the delta H of anything in its elemental state is going to have an enthalpy of 0. 0 kilojoules, if we want to be specific. Because the enthalpy of formation is talking about when 1 mole of compound is made. But here, if we're talking about an element, it's not made from other elements, so its enthalpy is 0, as long as it's in its standard state. So let's check this out. We see here that in order to find the enthalpy of a reaction, we can use the enthalpy of formation for various compounds. So we have this equation that looks a little scary, but let's break it down. This Greek symbol, sigma, means sum. So we're going to add pieces together. And what we're going to add is N, which represents the coefficient from a balanced chemical equation, times the enthalpy of formation of the products. And we're going to subtract the same thing, but for the reactants. This is essentially what we've been looking at the whole time. Every time we see delta, we know that it means final minus initial. So we're taking our products, which is the final, minus the reactants, which is the initial. So let's check out this example where we want to find the enthalpy change for the combustion of benzene. Benzene is C6H6. So since it's a combustion, we know we're going to have oxygen as our reactant. And we know we're going to make carbon dioxide gas and liquid water. So first things first, we need to balance. So go ahead and pause the video, balance this reaction. So you should find that the coefficients become 2, 15, 12, and 6. Now what we're going to do is look up the enthalpy of formation for each of these substances. Again, you can do that using your references in the textbook. For an exam, you will be given these values. You will not have to look them up. So first, let's look at benzene. We look in our references and we see that it has an enthalpy of formation of 49.0 kilojoules. Oxygen is an element, and it's an element in its standard state, so it's going to have 0. Carbon dioxide, now we're looking at the products. Carbon dioxide is going to be negative 393.5, and water is negative 285.8. Make sure that you can find all of these values in your textbook so that you know where they're coming from. Now we're going to use our equation. The equation starts with products, so that's what we're going to do as well. I'm going to start just by writing out how I would solve for this problem, and then we're going to plug in the actual numbers. But starting off with carbon dioxide, we take N, which is the coefficient, so 12, times the enthalpy of formation of carbon dioxide, plus, since it's a sum, 6, which is the coefficient of water, which is the other product, times the enthalpy of formation of water. That's all of my products, so that's my first portion, minus the sum of the same thing, but for the reactants. So for my reactants, I have a coefficient of 2 for benzene, so it'll be times the enthalpy of formation of benzene, plus, since it's a sum, 15 times the enthalpy of formation of oxygen. And there's my reactants. And I meant to keep it color-coded in blue, and I didn't. So we'll just do the brackets in blue so that you can see. This goes here, and these go here. So now we're going to plug in the actual values. So we're going to have 12 times negative 393.5 plus 6 times negative 285.8 minus 2 times 49 plus 15 times 0. So we can now plug this into our calculator and see what we get. So I'm getting a value of delta H of reaction equals negative 6,534.8 kilojoules. And so that would be your final answer. This is how we're getting the numbers for each reaction in a Hess's law problem. This is also a way for us to find the overall enthalpy without going through a Hess's law problem.